Hang in for one more minute till all the jetty are back. Sorry about that. I actually promised. America's here. I promised to wait for you. All right. Now we go. So, by now you've all encountered Paul, and since he was the chairman of my session, I was granted equal privilege, and so we give him the full 35 minutes and an extra 20 seconds because he's such a pleasant chap.
Thanks. I'll use the first 10 seconds thinking of what to say with the other 10 seconds. Well, fortunately, my colleagues this morning filled in a number of the background issues about cosmological radiative transfer. Thinking that it would all be covered in the big picture, I would focus on the zooming in to ever smaller scales to the sources of reionization, in which case there is a back reaction of the release of ionizing radiation on the subsequent release of ionizing radiation, which is what I mean by the universe strikes back. So there are a few big picture points, though, that I want to make sure we're all thinking about. Why we're studying this epoch? Well, what do we mean by the epoch of reionization? First of all, the absorption spectra of quasars have long shown that the intergalactic medium at redshifts less than 6 is highly ionized, with a residual neutral H atom concentration of less than 1 atom in 10 to the 4. Hence, the universe experienced an epoch of reionization before that. Thanks to the Sloan Digital Sky Survey discovery of quasars at redshifts greater than 6, we're able to plot the evolution of this absorption spectra due to the residual neutral hydrogen after reionization. And it shows a dramatic increase in the H1 fraction at the epoch of order redshift 6 as we look back in time, suggesting that the epoch of reionization has only just ended at a redshift not too far before 6. Adding to our evidence of the existence of an epoch of reionization is a measurement of the cosmic microwave background polarization, and the fluctuating polarization, which is coherent on large angular scales, tells us, as observed by the WMAP satellite, that almost 10% of the CMB photons must have been scattered by free electrons in the intergalactic medium before we observed them. This means the intergalactic medium must have been ionized much earlier than a redshift of 6, since only less than 5% of the photons would be scattered by the intergalactic medium since a redshift of 6. And therefore, in order to supply the electron scattering optical depth, the reionization must already have been substantial by a redshift greater than of order 11. So as Mitch Biederman told us yesterday in summarizing the cold dark matter scenario for structure formation, we live in a universe in which the structure formation is hierarchical, the smallest mass concentrations collapsing out of the background first and merging to make an ever larger mass object. Gravitational fluctuations are Gaussian random noise with a power spectrum which was close to scale free in the early universe, and then it transferred through the universe prior to the epoch of reionization to produce the characteristic power spectrum that we all start with as initial conditions. And when we follow the evolution of the structure just under the action of gravity, we see the production of this filamentary cosmic web. At the intersections of the filaments are quasi-spherical objects nearly in virial equilibrium, with dark matter dominating the gravitational potential, and on scales above the Jeans mass in the intergalactic medium, which at very early times is about 10,000 solar masses, the baryons follow the dark matter into these halos, and those are the sites of galaxy formation. The halos which are less than about 10 to the 8 solar masses, total mass, we call mini halos. Those are the objects which are believed to be the sites of the first star formation, the POP3 metal-free stars. They form there only if this metal-free gas is able to become self-gravitating by the action of hydrogen molecule formation and cooling. And the study of reionization is typically based on the premise that although those first stars form in the mini halos, the rise of the background of ultraviolet radiation from those stars includes radiation below the Lyman limit, which is capable of dissociating the hydrogen molecules. And before we finish reionization, long before we finish reionization, we have supposed that it builds up a Lyman-Werner band dissociating background capable of sterilizing the rest of the mini halos, leaving the job of reionizing the universe to the more massive objects, more massive than 10 to the 8 solar masses, which are able to use hydrogen line cooling to get to the point of self-gravity within the halos and star formation. And this is the premise on which most of the reionization, large-scale reionization studies have been done in recent years, with ever increasing sophistication, larger and larger volumes, and it's necessary to do extremely large volumes in order to get a statistically fair representation of the process and then predict observable consequences such as the redshifted 21 centimeter background, the kinetic Sunyaev-Zoldovich effect due to the scattering by moving electrons in this intergalactic medium, the scattering of the cosmic microwave background, the effect of patchy reionization on our ability to detect Lyman alpha emitting galaxies at very high redshifts, and so on. But in fact, that premise that the reionization is due to objects more massive than 10 to the 8 solar masses, which are the atomic cooling halos, and that the first sources of star formation are actually not important in finishing reionization, is very uncertain and subject to confirmation. So what I'm going to tell you about is how we go from the big picture and zoom in and zoom in and zoom in to that issue. And on the big picture, we will be able to take the approximation that the density is static, because the propagation of the ionization fronts that surround the first sources of ionizing radiation is highly supersonic relative to the sound speed of the ionized gas, much higher than 10 kilometers a second, and therefore outraces the hydrodynamical response of the intergalactic medium. So we are able to propagate the ionization fronts around many sources. Here I'm showing you a volume which is 100 over H megaparsecs on a side co-moving. The results here were the results of an n-body simulation that my collaborators Ilyan Ilyov, Harold Melema, Whaley Penn have run, involving 1,624 cube particles on a 3,248 cube grid of cells, periodic boundary conditions, Gaussian random noise according to the primordial power spectrum, and we're looking at a 20 megaparsec slice in projection. Curiously, we all made a decision that we would talk about things that had radiation coupled to hydrodynamics as our focus at this meeting, and the fact that when we propagate the ionization fronts as a sequence of times here around the sources which are the galactic halos in the static limit, which is absolutely a good approximation, because if we were to take account of the motion of the gas following the heating by the ionization front, we would not change the picture. we decided that that was somehow radiation, but not radiation hydro, although I think it really is. It's just in one limit. So, starting from that picture, this is what it looks like. If we assign to each galactic halo a constant mass to light ratio, and we have a certain efficiency factor, which I'm not going to bother to define, which says for each baryon in these galactic halos, how many ionizing photons they're released, based upon assuming that some fraction goes into stars, and the type of star determines in the lifetime of the star how many ionizing photons it will release. So this is a movie showing a cut through the simulation volume from redshift 20 to redshift 12, and the gas density is shown in green. I don't know how well these things are showing up in the neutral regions, yellow in the ionized regions, and the H2 regions are also colored red.
Paul, quick question. Do you have a feel for how much POP3 stars are contributing to this picture?
The minimum mass resolution here is about 1 billion solar masses.
Okay, so
Now, the statement POP3 stars has nothing to do with which galaxies host them. Okay, so these could be POP3 stars, but not mini halos. That's the distinction we want to make. Here, I tell you, I've located the galactic halos, which are each responsible for this ionizing radiation. And what you can see is a couple of things I'm not going to dwell on, but you'll notice the H2 regions only grow, even though the lifetime of the sources is, in this case, it's done in episodes that are only tens of millions of years long. And the reason is that as time goes on, more and more of them form inside the pre-existing H2 region. So it's not a case of where an H2 region forms, the source dies and recombines, and instead there's continuous expansion. In addition, the growth of the pattern has clustering in it because the sources are highly clustered. And wherever you see the most massive source around it in a biased distribution in space are clustered lower mass sources. Of course, the most massive ones are the least abundant. They are exponentially rising in abundance with time. Now, suppose I take a little corner of this box, which is one radiated transfer cell across, and in this particular movie, I guess this is 400 radiated transfer cells on a side. We coarsened the density field from the high-resolution and body simulation that was responsible for forming the sources and giving us the density field. So look at just one of those radiated transfer cells, and this is what it would look like if we zoomed in on it. And here we have a box which is about 0.5 megaparsec on a side. And what I want you to see is, first of all, the density is shown, the isodensity surfaces show about twice the mean density. I wish we could make it darker, but we can't. I hope you can see it. But what we've done is to locate all of the galactic halos, all the way down to the mini halo, the smallest mini halos, in this volume. And the mini halos are represented by spheres, whose size is the actual size of the virialized object, and whose color codes the mass. And the largest one is just under 10 to the 8 solar masses. There's only one of them in that volume. And this would be the source of the atomic cooling that leads to star formation. So assuming we suppress star formation in all the mini halos of smaller mass, that would be the one that was the source of ionizing radiation. So now we let it go, and just to show you where it's going to be, we light it up before we propagate an ionization front, which is a weak R-type front that propagates highly supersonically relative to the sound speed of the ionized gas. So first I rotate it so you can see the cosmic web. You can see that the mini halos are arranged in the filaments and on sheets of the cosmic web. And as soon as we stop the rotation, we turn the source on, and the ionization front, in a matter of a few million years, will propagate out to the edge. So this is the surface of ionization within which everything is ionized and outside it's neutral. And now what I want you to see is that as you peer through this, into this H2 region, you'll notice that the ionization front was stopped when it reached the mini-halos. And they produce shadows. And that's because the speed of the ionization front depends on the density of the gas into which it's moving. And when it moves into the dense gas in the mini-halos, it slows down to the sound speed of an ionized gas and has to make a transition from weak R-type to D-type ionization front, at which point hydrodynamical back reaction is going to take place, and that's the rest of our story. So, now looking inside a region even smaller than that, we identify a place where the first star will form. And now we are talking about mini-halo star formation. And we're going to ask what is the effect of the H2 region of that first star. So I need to remind you that simulations which include gas and dark matter and the cooling and formation of hydrogen molecules tell us that the first star is formed in mini-halos with a mass something under 1 million solar masses at redshifts greater than 20. And so we've combined a gadget SPH simulation of the cosmological density field which formed the first population 3 star with a high-resolution 3D ray tracing calculation which tracks the stellar eye front to follow the evolution of the first H2 region. And we're going to follow it during the lifetime of the star from inside the mini-halo until it ionizes the surrounding intergalactic medium, the local beginnings of cosmic reionization. For an isothermal sphere density profile of the mini-halo gas, which is, as Dan Whalen told us this morning, a good approximation to what the AMR simulations with very high resolution tell us is the site of that first star formation. 1D hydro calculations show us that the ionization front starts out as a D-type preceded by a shock, but eventually the ionization front races ahead, detaches from the shock front, and runs out of the mini-halo as an R-type front, leaving behind an ionized gas with a shock wave, and inside the shock wave, a nearly uniform density of isothermal gas at about 10,000 degrees. So the breakout of the ionization front leads to what has been called this champagne flow, for which there are numerical and analytical solutions. And the important thing for us in what's following is that we can treat this as nearly uniform inside the boundary of the shock, which we have an analytical solution for. So inside the shock-bounded wind of the champagne flow, the mini-halo gas is approximately homogeneous and spherically symmetric. We can apply the 1D analytical wind solution as our inner boundary condition, and outside the wind, the gas is nearly static over the lifetime of the star. So we can treat the radiated transfer in this static limit, where we do ray tracing and an ionization front tracking solution, which I won't give you the details of, as sufficient. So now I'm going to tell you about the propagation of this ionization front, starting with a box which is 280 kiloparsecs co-moving, represented by 128 cube SPH particles. Each particle has a mass of about 60 solar masses. The star is assumed to form at the location of the highest density SPH particle at a redshift of 20, a density of about 10,000 particles per centimeter cubed. And we calculate the propagation of the ionization front outward along rays. There are about 50,000 rays with 640 segments. It's a kind of adaptive pattern of rays. And along each ray, we solve this equation for the radius versus time of the ionization front, where Q is the number of, essentially the number of ionizing photons given by the number of ionizing photons from the source, minus the correction due to absorption, which is balanced on the ionized side by recombination. So we can count absorptions of ionizing photons by counting recombinations on the ionized side. Even though the process may be non-equilibrium, the equilibration time on the ionized side is actually very short. And the other thing I just want to bring your attention to, because it came up earlier, is that in the denominator here, we have the speed of light. And that's because this is the equation for the ionization front taking proper account of the finite speed of light, although in other problems we don't worry about that. So this is three zooms from the top, middle, highest level of zoom in terms of the size, the part of the box. The box that I'm showing you the contours in is 13.6 kiloparsecs proper across, and at time t equals 0, it's all neutral. And then depending upon whether the star that turns on is an 80 solar mass star or a 200 solar mass star, we have two examples. Stars live a few million years, and they create these H2 regions. And here I'm able to see through it into the region inside. To give you a slightly better feeling for that, I can rotate it. So it's not spherically symmetric, but most important is that when we zoom in, and I travel to a zoom that allows us to see on the inside, you will see that on this scale as well, just as we did on the larger box scale, so here I look at the highest level of zoom, and I rotate it, you will see that the ionization front is trapped by the neighboring mini-halos. So the question then comes for us to ask now is, when the ionization front from the first mini-halo, the two pop off, makes its way out of the mini-halo into the neighborhood and overtakes the nearby mini-halos, the question is, what does it do to their potential for star formation? Does it make them form stars that they wouldn't have formed without that help? Does it amplify the star formation rate, or does it kill them off as a source of star formation? So let me skip ahead so that I don't run out of time and just focus on that trapping issue. So the ionization front, here I now show you this trapping, the same that we saw in the three-dimensional image. This was the location of the mini-halo that formed the first star, and the color coding here shows that I have high-density ionized gas where these particles are. I have low-density neutral gas behind in the shadow, and I have very high-density neutral gas, indicating that the ionization front did not penetrate this halo. And we've done simulations of the evaporation which would result. I'll show you that in a second. But we know that the time it would take to evaporate this gas in this mini-halo is more than the lifetime of the star. So it is not going to penetrate all the way into the center. And there has been a recent literature on this problem, which included an attempt to simulate this problem starting from adaptive mesh refinement and formation of the star rather than SPH, but making the approximation that everything was flash ionized instead of properly taking account of the trapping. And it is interesting that when you flash ionize it, that dense gas recombines out of equilibrium and forms a lot of H2 molecules before it has a chance to blow away, and then it appears that you stimulate star formation. But when we saw that, as we already knew, the mini-halos would trap the ionization front, we then thought that's not really the whole story. That's not correct, and it has to be done with the back reaction. So we already knew, because when we were simulating the reionization problem on larger scales, we knew that the encounter of those large-scale ionization fronts, even during the major part of reionization, not this zoomed-in beginning, that when the ionization fronts encountered the mini-halos, they were dense enough to trap the ionization front, and they would be an impediment to reionization. They would block the path of those ionization fronts in every direction where they encountered one, and we could statistically count them, and we knew that this was actually a possibly major effect on reionization, because in every direction they were likely to encounter mini-halos. So we simulated that with two-dimensional radiation hydrodynamics, in this case, an axisymmetric calculation, with a source irradiating a mini-halo which was centrally concentrated, hydrostatic equilibrium, dark matter of gravity binding the gas, and we've demonstrated the ionization front trapping. A supersonic wind blows back towards the source as the ionization front slows down to D-type, preceded by a shock, and eats its way through the mini-halo. And here, I'll show you this in a movie in a second, but this is the sequence of temperature plots as the ionization front enters the box from the left, and ionizes and heats the intergalactic medium of much lower density than the dense mini-halo gas, enters the mini-halo, becomes D-type, and then gradually works its way down through the core, and the photoheated gas blows away, bounded by a shock, and then contact discontinuity, and so on. And just to show you that in motion, it only takes about a mega-year for the ionization front to reach the slowing down to D-type, but as a D-type, the supersonic wind blows out of the mini-halo back in the direction of the source. Shock heats the intergalactic medium as it sweeps it up, leaves behind a cold, empty shell of a dark matter halo. And it takes of order 100 mega-years to do that. So now it takes of order 100 mega-years, remember that. Lifetime of a POP3 star, one of these neighbors, is only 3 mega-years. So this was a different phenomenon. This said if I have that steadily driven ionization front coming from many sources, one that replaces the next, and it's steady, this will happen. But if I'm only asking for what's happening to the neighbor in the neighborhood, can I stimulate? So we went back then to this problem, and now we did this problem in 1D. Because we wanted to add the self-gravity and do the chemistry and the radiative transfer with enough resolution that we could see a tiny mass fraction at the center that might collapse to form the star. And so I'm going to show you the results of the high resolution but 1D Lagrangian radiation hydro simulations, where we took a 120 solar mass POP3 star that formed at a redshift of 20 inside another mini-halo in the neighborhood of the first one. We considered a range of distances between the source and the target mini-halos, which would have corresponded to the different mini-halos in the region of that larger simulation, ranging from a 50 megaparsec distance where a merger is actually taking place. It's so close that the mini-halo target is actually inside the primary mini-halo that formed the first star, all the way out to the edge of that neighborhood, which is a kiloparsec away. And another advantage of using 1D Lagrangian hydros is that we could blanket this parameter space in a way which we couldn't if we were doing, highly resolved, multi-dimensional simulations. So we're learning from this what we will have to do eventually in multi-dimension. And then we parameterize, therefore, the flux at the surface of the mini-halo target according to these distances. And the units on my plots are dimensionless. I take a 120 solar mass POP3 star. It releases 1.5 times 10 to the 50 ionizing photons per second. And if I were to place that at a distance of a kiloparsec, the dimensionless flux parameter would be 1.5. And it scales with distance this way. So I then considered a range of mini-halo masses from 2.5 times 10 to the 4 up to 8 times 10 to the 5 solar masses, and then 2 stages of evolution for the initial condition of the mini-halo. We know how mini-halos form, as the process of virialization leads to something like a non-singular truncated isothermal sphere with dark matter and baryons. However, no sooner does that collapse and virialization take place than the chemical evolution of the virialized gas leads to some molecule formation and cooling and compression. And so we take as two limiting cases the case where the source irradiates the mini-halo before it has a chance to evolve away from that initial condition, and another one where the neighboring star waits a few million years before it turns on and catches the mini-halo in a stage of advanced evolution. Phase 1, no evolution. It starts out with a molecule fraction of 10 to the minus 6, a residual electron fraction of 10 to the minus 4, and the temperature in the core is just the virial temperature of the halo. Thank you. Phase 2 is evolved for a few million years, which is a tiny fraction of a Hubble time, and it points up the importance of taking account of the synchronized evolution of star-forming mini-halos in the early universe, which is rarely done when you do highly resolved adaptive mesh refinement. You have to pick your target, and you zoom in and you refine and you refine and you refine, and you don't refine on that guy at the same time because it's too costly. But in fact, that guy is evolving while you're evolving too. And when you ask, okay, now I'm ready to feed back on him, you got to ask yourself, what's he been doing? And so that's what phase 2 is all about. In that case, the molecule fraction has risen to 10 to the minus 3 in some cases, while recombination has taken place, choking off the source of molecules. But that radiative cooling of the hydrogen has dropped the temperature in the core to 200 degrees, causing the core to compress by up to a factor of 20 in some cases. Okay, so now we have a rather complicated plot I have to explain. To summarize, it's easy once I explain it. But what we've done is to take, for each mass mini-halo, the outcome of its evolution in the absence of radiation, in terms of its ability to collapse and form a star within a Hubble time, versus in this case, if the collapse is delayed, is too long to form a star, then no star forms here with a triangle. Circles mean stars form. And then we ask, what happens to that mini-halo subject to different levels of ionizing radiation and dissociating radiation? And the size of the circle tells what happens to the collapse time. So if these circles are smaller than these circles, that means that it's sped up the collapse. If the circle's bigger, that means it delayed the collapse. And then finally, there's a dot in there because we discovered a new mechanism for inducing the formation of hydrogen molecules triggered by the D-type ionization front shock that penetrates to the middle of the mini-halo. So what you would take from this is that the minimum mass for forming stars was about 10 to the 5 solar masses, and that apparently turning the radiation on, since the circle here means it collapsed, and the circles here mean they collapsed, means that there was no the question of whether the feedback was positive or negative, which translates to collapse or not to collapse, the answer is they collapsed before the radiation was turned on with no radiation, and they collapsed anyway. On the other hand, with no radiation, they didn't collapse. If their mass was too small with radiation, they still didn't collapse. So that's why I said this morning that the effect, and this is just what happens if I take the more evolved payloads, it shifts by a factor of 2 the boundary, but it really hardly changes that neutral outcome. So I'm just going to give you a couple of examples to bring that to life. So, for example, a target mini-halo of 2 times 10 to the 5 solar masses would, in the absence of radiation, take 31 megayears to collapse and form a first POP3 star. With radiation, with a flux at a distance of 180 parsecs, which was the stopping distance I showed in that three-dimensional rotating view of the H2 region. That's the distance of that mini-halo that stops. It turns out that in the presence of that radiation, the collapse is expedited by a factor of 10. It will now collapse in under 3 million years. And under 3 million years is interesting because the lifetime of the POP3 star is longer than that. So that says that while it may be true that it was going to form a star anyway, now it forms the star faster than it would have, and it therefore forms the second star in that neighborhood while the first star has not yet died. And that's a novel effect. If I were to show you the animation of the lines, of the line cuts, where I have plotted versus radius towards the center, I plotted the velocity, I plotted the H2 fraction, the electron fraction, the H1 fraction, the temperature in degrees Kelvin, and the density in grams per centimeter cubed, and I'm going to show you what I mean by collapse. So this is the initial condition, we let it go, the ionization front works its way in, slows down to a D-type front, and has a shock front in front of it that detaches. This shock front actually runs up the hill and accelerates to producing a temperature of 10,000 degrees, briefly, but enough to stimulate the presence of extra electrons that boost the hydrogen molecule abundance. That's the shock-induced molecule formation mechanism. And with that extra molecule abundance, the temperature drops to a couple hundred degrees, and the density reaches 10 to the 8th particles per centimeter cubed, at which point 3 body reactions would take place, which we don't have in there, but we know that the collapse would be inevitable. So we say it's reached the point at which we know it's gravitationally collapsed, the star has formed. And I could show you other examples. The last one I'm going to show you, though, just to skip ahead, is what happens if you have this piece merging with the mini-halo, and it's within 50 parsecs. In that case, you might think, it's so close. Surely that POP3 star is going to shut down star formation in that object. It's within its own mini-halo. And so let's take an example of something, 5.5 solar mass object merging with the parent mini-halo that made the POP3 star. With no radiation, it would take only 11 megayears for that lump, merging as it is with the mini-halo that formed the first star, to form its own star. But with radiation, at a distance of 50 parsecs from the first star, if you ignored H2 self-shielding, that's really what the point of this. I'm going to show you with and without shielding. If I didn't take proper account of the need to take the opacity of the Lyman-Werner bands of the H2 molecules present into account, I would find that I delayed the collapse of that merging mini-halo for about 50 megayears, which is a short fraction of a Hubble time, but nevertheless is long enough that the first star would long since have died. If I instead put the self-shielding in, I find that in the presence of the self-shielding, the collapse is expedited to 1 megayear, which means that the second star forms before the first star dies. So we first saw this, we realized this is the first example we have of a calculation which shows that when a single POP3 metal-free star forms in a mini-halo, the first in its neighborhood, if it does so while mergers are taking place, as they typically are, it is possible that in the same mini-halo another star will form before the first one dies. And so now to summarize, the ionization front was trapped, transformed from R-type to D-type, preceded by a shock front. All the ionized gas, that is to say all the gas that was originally outside of the trapping radius, is evaporated. A precursor shell of hydrogen molecules forms. I didn't focus on it, didn't take the time, but it leaves the ionization front, stimulated by partial photoionization, which Dr. Umemura also talked about this morning. And one might think that that would be an important source of self-shielding for the core. But what we find is that even more important is this shock-induced formation mechanism, where the shock accelerates surprisingly up to 10,000 degrees, just enough to trigger extra collision ionization, extra electrons, which stimulate molecule formation, and then the molecules cool the core. The fate of that neutral core is determined primarily by the response of this ionization front-driven shock. And when you compare it to the same halo without external radiation, the molecular cooling and collapse can be either expedited, delayed, unaltered, or reversed or prevented, depending upon the distance to the source, the halo mass, and its evolutionary stage when it's caught by the first star turn on. But roughly speaking, halos destined to cool, collapse, and form stars without external radiation will do so even when exposed to the first POP3 star in their neighborhood, while those that cannot will still not be able to do so. Previous reports of strongly positive or negative feedback appear to have been overestimates, and surprisingly enough, not only can nearby mini-halos still cool and collapse to form stars after they're irradiated by the first POP3 star in their neighborhood, but they can sometimes do so within the lifetime of the first star. And I'll stop there.
Well, we have minus 20 seconds for questions. So, please make them not lengthy.
Maybe you said it and I missed it, in which case you're getting another 10 seconds. How do your conclusions depend on the hardness of the photon spectrum?
We take that into account. So I would say not strongly, except that it's a star, it's not a quasar. I haven't done this problem with a quasar, I can't tell you. But POP3, 100,000 degree black body, has...
No power laws or anything?
No.
Okay, thank you.
Paul, we discussed this earlier, but I'm pretty sure that shock acceleration of the gradient is not physical. I'm pretty sure that that's an effect of your coordinate mesh and the focusing of radiation that works.
Well, we disagree.
Yeah.
Okay, let's leave it there. You guys fight it out.
I want to answer you with one sentence, and that is that the same temperature due to a shock that accelerates in the axisymmetric calculations, which are not 1D and don't focus to the center, also gets up to 10,000 degrees.
But have a hard coordinate center, right? Isn't the halo in those 2D simulations also centered on a...
You're going to make me feel bad, but this is a wonderful conversation. I'd love to hear more. But...
And we have time for discussion.
Nothing worse than that.
In the nearby universe, massive star formation is always multiple. Why do you form single stars?
Well, the simulations, this is actually one of the motivating questions here. The simulations report the formation of a single star by refining until it looks as if there's no further fragmentation and it looks like there's only one protostar. But they don't ask what's going to happen within another 1 million years, another 3 million years. So when you say massive stars don't form by themselves, you don't mean they form within 10,000 years of each other. You mean they form within 1 million years, or 3 million years, or 10 million years.
What I mean is simply, if you collapse matter up to a point, usually you always have fragmentation, so you form, let's say, 3 or 4 stars in a very close vicinity to each other.
But within what time period? That's what I mean.
At the same time,
Same time.
yes.
I mean, all the massive stars we see are multiple. And so I'm asking, why is no star single?
Yeah.
The angular momentum conservation is valid also in the early universe.
Yes. So I guess the answer is this is a result that's not my own. It comes from the people who've done the adaptive mesh refinement simulations of the first star formation. The only contribution I'm making to that story is to say that by virtue of their refining it to the point of only seeing one star form, they have not been able to ask the question of what's happening nearby. And we're trying to address that.
And the big difference is that there are no metals to cool. So this thing is actually cooling slowly, and it's cooling in almost allostatic equilibrium, so it doesn't fragment the same way as today.
But still, the angular momentum should play a role. But we can...
It seems to have a small angular momentum.
Sorry about that. Mitch,
Well, I was going to ask about the angular momentum. There must be a certain fraction of these that are going to have enough angular momentum, so that's really going to affect the collapse. And can you?
I'm sure that there is a scatter in that property, but
There's calculations that predict the distribution.
the truth is the only simulations that have gotten to the density of seeing the protostar or something that's going to be the protostar, claim to see very little angular momentum. They don't make disks. That's the surprise. That doesn't stop analytical modelers from putting disks in, as they have done, but the simulations don't show
I
it.
thought Abel's recent simulations were showing some angular momentum effects, what John Wise was doing.
You have to build it in, I think. Oh,
All right. So we, come to the last speaker, and he will tell us about LCD multimedia projector. Let me go and,
No, you're welcome.
Oh, I just got rid of his comments.
okay, just, fine. These guys got a CPU. So that was this one. Yeah, the CPU is.
All right. It's a pleasure to finish this very interesting workshop, and all I can do is try to give a pep talk and encourage further evolution and optimization of methods and radiated transfer. So where are we headed? What do we want to do? Well, of course, we want to include radiation as an active ingredient and also as a diagnostic tool whenever it's relevant. What can we do? Well, the optimistic answer is we can do the same as above. But of course, a more realistic one is that we really have to strike a balance between relevance and cost. The general belief is that radiated transfer methods are expensive, and I will try to convince you that that can be negotiated. But let's first just classify the various problems, because this differs really very much, as we've seen during these 3 days, between the three groups that have been giving presentations. Jürgen, you were presenting diagnostic methods, and in some cases that includes really computing an energy equilibrium, but in a static situation. And in other cases, we want radiated transfer to be part of the energy balance, so it's a time-dependent problem. And a really difficult one is scattering. Even as a diagnostic problem, if scattering is really important, then it's a 3D problem of similar difficulty as non-LTE problems in 3D. And those probably are the ones that should be at the bottom of this table, being considered the most difficult one. Hello, Dan. The context, we'll see in the context, cosmology, accretion disk, star formation, planet formation, stellar surfaces. But I'd like to just take a little detour here and comment on Ed's complaint about the radiation hydro name. We really have a problem. We don't really have any good names. You suggested photofluid dynamics. Well, that can work, I think, for the next generation who didn't grow up with cameras where you had a dark room in the basement and you had photofluids. Now, in the next generation with the digital cameras, it's okay, perhaps. But the least I can do is to protest against the hydro. It really is MHD in most of these cases. The accretion disks wouldn't really work without MRI, and the heating from magnetic effects is really the key to understanding X-ray emitting disks. And in star formation, At least I and my collaborators are convinced that the magnetic field even determines the shape of the IMF. And jets wouldn't work if you didn't have magnetic fields and so on. In planet formation, probably you wouldn't form the same type of disk if you didn't have magnetic fields during the collapse of the core that made the star, that made the protoplanetary disk. So you're even there, even if perhaps in the later stages the disk is too cold to be actively immersed in disk. And of course, in the stellar context we have chromospheres and chromospheres, and in a sense it affects even cosmology, because the absence of magnetic fields may help make the IMF different in that context. So let me just comment on a few things in each of these categories. In the classical 3D photospheres, some of my acquaintances in other contexts, for example, Richard Klein, has never understood how we can get away with so few rays. But the explanation is that it works because we have a rather uniform radiating surface, and it's nearly flat. It doesn't work so well when you have magnetic structures that are deep, narrow and deep, which we have some examples of. But the advantage here is that you can then include several frequency points, and it's really the number of angle frequency points that is the cost factor. And with current codes, there's a sort of 50-50 split at around 50 angle frequencies. In the context of chromospheres and corona, the focus now changing to doing non-equilibrium ionization and mocking up something that approximates non-LT line transfer effects on the thermal coupling. There are a number of radiative transfer issues in star formation that have not been opened up really yet. In order to understand really molecular cloud formation, I'm convinced that we need to do proper radiative transfer calculations, where we understand that at a certain density, a cloud which is scooped together by more or less random effects from earlier supernova shells expanding and colliding, becomes dense enough to self-shield, and then things really develop very quickly, and it cools down to its 10-degree nominal temperature. Of course, as we've seen in the last few talks, extra regions that are peeking through in the host and the cheese are very important, and try to eat into the existing structures. We haven't really had a talk about massive star formation with details, but as you know, the Berkeley group is doing fantastic work in that context. And something that is close to my heart is to understand the very short and therefore hitherto unobserved phase in star formation where you go from class 0 to class 1. So by definition, more than half of the mass goes into the star from being in the envelope on the disk. And that must be close to the point in time when the disk to star mass ratio is largest. So that's where we should really expect instabilities of the disk to be important. The importance of, in the future, doing radiative transfer in the molecular cloud formation context can be illustrated very nicely by taking one of the many fantastic plots and animations produced by Miguel Abilias and his collaborator Rashford. This is from a simulation where you see on the right you see magnetic field, and on the left you see density. And what that class of scientists are trying to produce is a self-consistent simulation of a sizable chunk of the galactic disk with energy input from supernova creating the structures that then form the stars that keep the thing boiling. And things indicate that really is what's happening, because you can produce self-consistent scale heights and reasonable results with that method. And some people really argue that the dynamics of the spiral galaxy that we live in is important. That may be. It may be somewhat important, but we just have to look at the large Magellanic Cloud to realize that it wouldn't really help there. There we really need to have a self-consistent supernova-driven environment. So here's a little animation from something a PhD student did a year ago, which does not include radiative transfer. And here you simply have to mock up what happens by saying if the density goes above a certain threshold value, you have an approximated self-shielding. And what happens then is already very intriguing. I'm sorry about the light again, it's difficult to see. But this is a time evolution. So star formation is being simulated or emulated by a recipe here. The scale is too large. The scale is 40 parsecs. So we can't really study the formation of individual stars. But we do the same thing that galaxy formation people do. When the density is high enough, we declare star formation and make stars according to the IMF. And a few of those stars are massive enough to explode, and they explode, of course, after a time delay. And we realized when we did this job that the time delay is very important, because it means that the massive stars explode outside of the dense structures where they form. They're not likely to remain in the same dense structures for those 3, 4, 5 million years before they explode. And the impact of the explosion is much larger when they are outside of the dense medium than if they're inside. And just to really impose or impress on you that the statement that the interstellar medium is turbulent and can be described by turbulent statistics is not just from theory. A number of diagnostics from observations show that that's really the case. Here's one, for example, showing the structure functions in Perseus and Taurus, and I don't have to go into details. But I would like to point out the fantastic difference between hydro and magnetohydro. You can even see it immediately in a visualization where here the projected density from snapshots of driven turbulence at 1,000 cubed are being shown. And it's a logarithmic grayscale, so we can see a number of levels down. And clearly, visually, there's a big difference between the left-hand side, which is hydro, and the right-hand side, which is MHD, with fewer structures, and that is reflected in the core mass functions of those two cases. The core mass function of the MHD case has a slope very similar to the salpeter IMF slope on the right-hand side, whereas the hydro has a much steeper slope. And as a curiosity, we've even used the difference between the different numerical codes to investigate this question further, because otherwise you'd expect that this power index is a thing that nature decides. You have a driven turbulence situation with a certain Mach number, that's not really negotiable. You should have a certain power index, whatever it is, we may not be quite certain about, but there should be only one answer to that question. But if you make this experiment with, for example, the Zeus or the ENSO PPM method or my code or SPH, none of them actually give the same result. And the power index is almost a factor of one steeper with SPH than with any of the grid codes.
Sorry, almost a factor of 1?
Sorry?
Order unity, it means.
Sorry?
He's worried because you said order a factor of 1. You mean order unity.
Okay, it means that the slope is 2.7 or something instead of 1.8. So, an order of magnitude per magnitude.
Are they both using
Now,
the same turbulence?
that can be taken, if we just ignore the reason why that is so, we should worry about that some other time. We can take that as an empirical experiment set. So we have one experiment set that has a steeper power law spectrum for whatever reason. And if we test the idea that that influences the Clump spectrum, it works. So the same
formula that you otherwise only have one value to put into, and you're not so impressed that it works. It really works in different cases. Now, here's an illustration of what they've done at the San Diego group, which is quite impressive, actually. Here's a zoom in on a 5-parsec cloud, where if we analyze the density structure and try to put stars where they should be able to collapse, we get something like this. And if one zooms in onto something that forms disks with the size of the order of the solar system, this is what we see. First, here's a scale of about 1 parsec or so. There's a little dot here indicating 100 AU. You can't really see 100 AU yet. And the time is running for about 4,000 years, and you cannot see much happening. It's sort of changing a little bit here in the filaments. But if you zoom in to something where 100 AU starts to become a little bit more than a dot, and look for 7,000 or 8,000 years, you can see much more happening, and you start to realize that the interesting thing is happening in small clusters. Another factor of something, and we're now on a scale where 100 AU is clearly visible. And now things appear to be happening much faster. And we can see that there are interactions between disks, for example. The two frames are just projections of the same situation, different axis projections. And if we zoom into a scale where this is now 100 AU, which is sort of the size of Pluto's orbit or something, we can see a disk covered by this AMR simulation. Of course, it's not quite realistic, but it reminds us strongly that when the disk formed, it didn't form in isolation. It wasn't a nice disk. It formed with stuff coming in at all kinds of angles and with not the same angular momentum vector even as the disk tries to have initially. So these disks that form protoplanetary disks, they form under busy conditions, which should be remembered when one tries to model them. And planet formation also contains a number of radiative transfer issues. We need to understand the cooling and structure of internally heated disks. And you can look for my name on AstroPH. I didn't remember to put the number on, but we published a paper recently where we compared different methods of doing radiative transfer in planetary protoplanetary disks. You may know about the conflict between Alan Boss and others about whether convection is important or not. That has very much to do with how you treat radiation at the surface. And in our case, when we have a smooth transition between diffusion in the interior and something which is a reasonable approximation of radiative transfer at the surface, there is no convection in the disk. Another topic for radiative transfer in that context is external illumination of either flared disks or, fantastically important really, is that most of these disks form in also busy conditions where there are OB stars nearby. This picture has been around for a number of years on the web and so on, but it was only in 2004 that Hester pointed out that one of the horns up here really has a disk and a jet at the tip. So here is a thing trying to become a protoplanetary disk, and it's really in an environment with a heavy extreme UV flux from some stars sitting up here. Now, we've heard about these efforts in cosmology, which are really impressive, and here's a picture that we saw just in the last talk. So far, what has been published has been diagnostic radiative transfer, if I understand correctly, with downsampled grids from the fantastic 3,248 in the dynamics to are still rather okay, 406 cubed in the radial transfer. The methods in cosmology are different than the methods that we're used to, but still there are very nice overlaps. And I'm particularly impressed by a method invented by Alex Rezumov, which uses something I like, namely parallel rays. And I'll tell you in a while why I like parallel rays. It's very similar to the authentic radial transfer method we heard about in the morning. And it's an adaptive mesh method. So whenever you have a refined region, you add some more rays, and you only keep them for the extent of the adaptive region. I should have pointed out that this is really for diffusive flux, diffusive radial transfer, which is a rather different affair compared to the discrete sources that we've heard much about until now. Of course, in this case, everything scales with the number of cells and the number of angle frequency points. And the key issue is, what is that scaling constant? How many microseconds or nanoseconds does it take for each angle frequency in the radial transfer solution? And what Alex does is to choose a set of angles from the heel pitch method, and then he's investigated how many directions do we really need to get a reasonable picture. And just visually you can see that if you use too few angles, you get these artificial streaks, of course. But he concludes that you need at least several hundred rays to each point. And that starts to become demanding. If that implies that it takes a factor of 10 longer than only Hydra and MHD, well, it's a pity. So what can one say about that? Well, there are other methods very similar. For example, this one by Recourse, which is again a long characteristic method. There is a bit of a difference, and that difference is interesting. Let me show this one again. See, what Razumov does is to say, for every ray, I decide which axis is closest. And then I consider this a plane parallel propagation, and I interpolate only to a point on each plane. So one doesn't consider these intersections of other axes. That's a great speed up, because it means that all of the interpolation coefficients in those planes are identical. You only have to compute those coefficients once, and you can apply them to the whole set that has the same inclination. And doing it like that requires a bit more work. I don't know how much, and we can talk about that afterwards. But another interesting thing here is what to do between domains. These guys were the first ones to point out, after a paper that we wrote, that one doesn't really have to do radial transfer piece by piece. If you compute radial transfer locally, and if it's a problem that doesn't couple to the ionization balance, for example, then the problem is linear, and you can really scatter gather from the whole volume to each domain directly. Not that it really matters much, because even if we do it sequentially in a method that we published a couple of years ago, it still doesn't destroy the scaling at all, because it's such a small number of values that are communicated. It's just phases. It gets tougher in AMR, because there are many small domains. So if one wants to apply this in AMR, one has to improve. But it's just a trivial thing. It's just simpler to do it piece by piece instead of globally. So here's one example of the timing issue. Here's an example where the method scales nicely, and where actually we see that the radiation itself is the smallest of the time requirements, and that the hydro in this case is taking most of the time. That's good. it means there is room for better radiation. And here's another plot showing the relative importance of the ray tracing, the communication, which is this line. So here it starts to become irritating at a little under 100 CPUs. So it's these issues that I want to comment a bit upon explicitly. And I'm taking as an example the pencil code, which is not my code, but it's Axel's and Dobler's and everybody else. It's a great community effort, that thing. So there was a little bit of confusion about that yesterday. In the pencil code, as in many other unigrid codes, for convenience, one is taking fixed directions. In this case, 13 rays. I think we should sort of distinguish between rays and ray directions. There are 2 directions along each ray, so there are 26 ray directions and 13 rays in this case, namely 3 along the coordinate axis, 6 phase diagonals, and 4 space diagonals. And why is that convenient? Well, it means you don't have to do any interpolations. And interpolations can actually take longer time than the radial transfer if you have a fast transfer method. And as I understood from Bernd in COBOL, the inclinations are arbitrary, but the directions are still in phase planes. And in Bob's and my code, we have random directions, we have the Gaussian quadrature set of angles, but we rotate the rays, so we sample the angle space from parameter to parameter. That's really a great idea that you can apply in many other contexts, because if you think of the time constraint on the time step, the Courant condition, it applies somewhere. So somewhere on the whole mesh, you're changing things a good fraction of a mesh, you're transporting things a good fraction of a mesh. But in most of the mesh, things are really moving much more slowly. So for example, 10 time steps, not much is happening with the location of most of the structures in 3D. And therefore, if one randomly chooses directions, then effectively the angular resolution can be 10 double compared to the resolution per snapshot. You can take 50 angles, and then over 10 snapshots, you really sample 500 different directions. So I come to the speed issues, because that's of course central to the question: how many rays can one use? How many angular frequencies can one engage before the CPU time is doubled, for example? That's a good measure. And this is, as I mentioned, particularly urgent in diffuse situation with a clumpy medium such as the interstellar medium or a molecular cloud, where furthermore we really need to do multi-frequency radial transfer. The heating is through the external UV field, but the cooling is through all kinds of other things like dust that should be represented with a few frequency bins as well. And doing this correctly is necessary to really quantitatively get molecular cloud formation right. So, the good old transfer equation for intensity looks like this. And there are interesting alternative formulations. First of all, most of the time in the stellar atmosphere community, one writes it the other way around, so like this. That's because optical depth is growing in the other direction. But if you take it in the natural direction, and specific intensity in one direction is I plus, and S is the source function, then this is a very simple equation. And the complementary one for the intensity going the other way, but counting the same direction of tau, is this one. And it has a formal solution, which one can use. I can use it in 2 different ways. One can use it by realizing that the distant part is really completely independent of the local part. And one can compute the local part in complete parallelism, and then communicate the distant part afterwards. It also is very useful as a direct method because it's very accurate. This can be solved very accurately, independent of delta tau, really. You can take a very large interval in optical depth or a very small one, as long as the source function is smooth. The source function is, for example, second order. If it's well disturbed by a parabola, this can give you a really good and accurate solution. And I'll show you what it really looks like in a while. The slowness of the exponential is a drawback, but as I'll show you with examples, in some cases that can be avoided because the CPU might have a specialized routine or a specialized hardware part for doing exponentials. Perhaps because it's tuned for doing foggy things in games and so on. It's often these game evolutions that we can benefit from. Right, that's the basis for domain consideration. That's what I mentioned before. However, it's almost always more useful to take the net intensity, the difference between intensity and source function. That's what we really need for heating and cooling, for example. And if one doesn't do that, one can quickly get into problems with numerical round-off, because the intensity goes to the source function as, the difference goes as e to the minus tau, and that can become very badly described by the usual single precision numbers. So if you replace the intensity with this Q instead, the transfer equation looks almost the same, but instead of a source function, you have a derivative of a source function with actually the same sign in these two cases. Now, if we have second order source function S, it means that the derivative is a linear function. And the solution then, the formula solution is simple to write up. It contains these three coefficients, e to the minus delta tau, 1 minus the same, and this combination is still containing e to the minus delta tau. It's only necessary to compute an exponential once. Furthermore, the same coefficient appears in the reverse transport, of course, between the same 2 points. So one exponential computation can be used twice, and that helps a lot on the speed as well. So the direct solution in the form of Fortran statements is actually very simple. It's just 2 lines of code, essentially. The problem is that these 2 lines of codes are recursive. So the result depends on the previous result. And for a while, that was a huge problem when we had Cray computers that didn't vectorize and such things. And then for a while it wasn't a problem at all because we had scalar CPUs. Now it's again a problem because there are optimizations, the streaming optimizations on Pentium and Opteron CPUs that really can speed this up with a factor of 2 if they're allowed to see something which is not recursive. So how do we turn something which is recursive into something which is not recursive? Can that be done? It's completely trivial, of course, because you can insert another index which simply numbers everything. So you have an array, but you can then put in all the other arrays that are parallel and loop over the redundant index first instead of the recursive index. And that makes the compiler happy, and it will speed up your thing with a factor of 2, actually. But first, this remote communication, how you parallelize things in with MPI. Well, it's a thing that's illustrated very nicely by this plot from Kobe's paper. Suppose I have a source function which is a smooth function. Now, if you solve for the local heating rate, assuming nothing comes in the local domain, you get, of course, something which is discontinuous. The intensity at the edge of one really should go in as a boundary condition for the next one, but it also should have a contribution from this one, attenuated by the entire domain in between. So every local domain should have contributions from all the domains upstream. And that's rather simple to do, and if you add those things in, you of course get the smooth global heating rate. And you've done now something which is good for parallelization. Most of the work has been done completely locally. And this includes, of course, interpolations to source function and opacity and so on. And only these boundary conditions have to be communicated. So the way it works is that you first solve this thing formally on all the local CPUs, and then if there is an external boundary condition that has to be added in, and then you just propagate through, and you have the whole thing computed. In the passive code, that scales enormously well. You can see that going from one CPU to 128, there is only a, 20% difference or something. But we can also see that even though the scaling is great, the actual radio transfer speed is not that great. It could be improved upon greatly, in fact. You can see that there is more than a factor of 2 when we go from no radio transfer to 14 ray directions, so really 7 rays in my notation. And that means that the time per ray, not per ray direction, but per ray, is about 300 CPU nanoseconds per point on a 2 gigahertz opteron. And I will tell you that can be pushed down to 12 nanoseconds per point. On top of that, you will probably have a dominating contribution from interpolations, or at least a similar contribution from interpolations, but one can get down to something like 20 to 30 nanoseconds per point. And what should that be compared to? It should be compared to what it takes to do MHD. And MHD typically takes at least 3 to 5 microseconds per point. And we can then conclude that properly optimizing thing, one can afford at least 100 rays, and maybe 200 rays without doubling the computing time. And that's really a good starting point for doing, for choosing a good balance between relevance and cost, that I was started to talk about. But to get there, you have to go way back in radio transfer again, and drop the integral method, and instead use the so-called Fourier method. What does the Fourier method do? Well, it changes, it transforms first-order differential equation to a second-order differential equation by a trick. It adds the two intensities going left and right, and it subtracts them. So we replace two quantities with two linearly dependent quantities. And it's then not difficult to figure out that the equation for P is the P d tau is equal to R, like so. And the equation for R is the R d tau is equal to P minus S. So if you put those two together, you get a second order differential equation which says the second derivative of P is the same as P minus S. And that's a differential equation that is very well conditioned. Even though you'll take huge steps in tau, it doesn't give you bad results. In fact, it gives you something which you can immediately see here, that in the limit of large tau, and if you have a smooth S, it gives you that the difference between P minus S is proportional to the second derivative of the source function, and that's exactly the diffusion approximation. So for a quadratic source function, it gives you the correct limit at infinite optical depth, the diffusion approximation. And it turns out to be very stable also in the limit of low optical depth if one uses a trick that Bob taught me years and years ago, decades ago. Even in this case, one really wants to use the difference instead of the intensity itself. And one can play exactly the same trick as before, introducing the difference P minus S instead of P, and then the equation turns out to be this one. So instead of the source function, you have now a second derivative of the source function, and that's excellent. So this is the equation to be preferred for this reason. These are the actual speeds of the various methods on computers that we would use today. If somebody wanted to make a cluster today, the most cost-effective one would be to buy an Opteron cluster with quad CPUs, 2 of them on each board, and as many as you can afford. That is the most cost-effective one at the moment. But on the other hand, cost is not always the factor. Several, I would say half a dozen of the people here, or maybe more, are computing on the Columbia cluster at NASA Ames. So I'm including also the times for Columbia, which is an Itanium CPU, an SGI Itanium CPU. And what's particular about that CPU is that its pipeline is not dynamic. So the compiler really has to figure out, while it's compiling, how to build the broad, I don't remember how broad, but a broad set of instructions to keep the pipeline busy. And the consequence of that can be seen in these numbers. On the Opteron and the recursive formulation, the integral method is actually faster than the Fourier method. Whereas if you go to the one with a redundant index, the Fourier method is faster by a factor of 2. So on an Opteron, the speed can be 13 nanoseconds per point, array, easily. On the Columbia, the integral method is really slow, and that must indicate that an exponential is expensive on an Itanium CPU, probably because it's not used for games. And there's not much to gain also from going to the redundant case from the recursive case. There's a 20% change or something. But still, it's a factor of 4 or 5 slower than the fastest method. So the bottom line here is that on both machines, on both types of CPU, you can achieve essentially the same speed, and to do that you have to use the Fourier method. All right, I just want to add a little remark about node wavefronts and other aspects. So as I said before, when radiative transfer is handled separately, it's actually not necessary to use wavefronts. So wavefronts would be this. You first have to compute the boundary, and then you have to do the next, and so on, and only communicate in the ray direction step by step. As we heard about in the talk in the morning, that can be alleviated by launching the next set of computations before the first one is done. But nevertheless, this is not necessary really in that case. One can do the whole thing at once just by a step of the other operations, as pointed out by Rikorst and company. But in cases where radiative transfer and ionization are handled together, this cannot be done because, as somebody was pointing out just in a talk today, you have to do this in a causal direction. So you have to know the ionization balance in one cell before you can go to the next one. I'm not aware of what the impact is on how it parallelizes and how it scales, but I would guess that it can be handled by doing most of the things still in embarrassingly parallel mode. Everything else, interpolations of capacities and source functions and bringing the result back to the energy equation, lots of things can be done independently of the communications. So I would guess that even then it's not a big deal to do communications. And we should always realize that things are getting better all the time. CPUs are getting faster with a factor of 2 every 18 months. But disks are actually getting cheaper with a factor of 2 every 12 months. And networks are getting faster with a factor of 2 every 9 months. So networks and interconnects are becoming less and less important. We shouldn't really worry about communications that were worrisome some years ago. Most of the clusters that you buy today would have InfiniBand on the board, without any large cost other than for the switch. So to summarize, radio transfer is really important and crucial in a number of aspects, subfields, some of which have not started to become harvested yet. But they're there, and they're available. We can do them. We just have to stay close to the optimal point of network speed. So, in almost all of the circumstances we can imagine that radio transfer is important, it's also doable. That's my pep talk. But speed of the computation and both of the transfer and the interpolations, and that's what I forgot to mention then in the end, that when the transfer itself is getting so cheap, then you're forced to worry about the next thing, and that is the interpolation process, which is much cheaper if you can reuse the same interpolation coefficients more than once. And that's why I pointed to the parallel ray case as really optimal for performance. And as I've illustrated, the optimal performance depends very much on whether the CPU is designed for games or not. So, in conclusion, what we want to do is to include radiation as an active ingredient, and I wouldn't even have to make this point. It's been demonstrated by almost every speaker at this workshop that it can be done, and it's giving us really interesting results already. We just have to live with this need to always try and optimize the methods. Thank you.
Well, thank you for giving us the program for the next meeting. I hope Axel's taken notes and is starting preparations. We'll be ready to come back. Are there any questions for Oka at this moment, or did you cover it all? Now, don't you start another fight.
Oh, I wasn't starting the fight last time. I was just raising concern. The idea of using gaming processors is one that perhaps, sadly, is gaining momentum at Los Alamos. What's your take on the use of these fast?
I just heard about rumors using PlayStation CPUs. Is it really serious?
Yes. The designers have insisted that they meet a certain benchmarking performance.
Tell them about the serious efforts in Japan. They can't really match that with PlayStations.
Yeah, okay.
Tell them about first. But how would they communicate? What would the interface be to communications?
That I don't know. The main thing...
Can you buy hyperband for PlayStation?
Well, the main issue, I think, is that these systems have almost no cache, maybe on the order of 20 kilobyte cache, and so we would have to rewrite all of our codes to be able to run these systems, and nobody can afford to do that, so we're not sure what's going to happen.
No.
So
they could buy 10 and...
Well, as computers, there's...
Maybe you stand up and shout to the group, because...
I'm sorry, well, at Los Alamos, the computer scientists actually tend to drive procurement of machines, which doesn't always serve the application scientists well. And so this is kind of a disconnect we're facing at the lab. And they're the ones who are championing the use of very fast processors the compute is essentially free, but all of the codes, millions of lines of codes in some of these would have to be completely redone and re-benchmarked. So.
As I know Paul Woodward, in that TPM version, I think he's sort of sitting making a cell-processor version, which is the PlayStation processor. So I think that's
so when you repeat the
right
question,
now.
I couldn't hear it.
So, TPM might count in the version for that?
Repeat the question.
What do you think? I'm sorry, I didn't hear the question. Could you
I didn't quite get the point, no. What?
No, the processors are there, but people are working on putting hypercodes on that. So
Yes.
There will be hydrodynamics, at least on no radiation transport, as I'm aware of.
But is it a serious effort where they also consider all of the peripherals? I mean, you have to have a suitably
that
fast...
is the next, it's not the terror, but the petascale computer will be very likely will be perhaps will be self-contained.
Okay,
It's not just a desktop, but the
okay.
next really big thing can be one of those. I mean, some 100,000 or something like that.
It's just the experience that if you try to build up say a local computing center, as important as having good performance is to have stability, to have something which is well proven and that experts can fix if it doesn't work. We've had bad experience even with IBM as a supplier. The InfiniBand didn't work, and it took them quite a while to fix it. So you wouldn't want to buy game toy pieces and put it together locally, and nobody really had the big view and the responsibility.
Services that come on special boards that's really meant for game special and the real thing. And then they're really expensive.
Okay.
Still eat and you cancel and you think,
Okay.
if you have to dedicate.
Okay. So they've been sold by specialized companies that really take the responsibility of...
IBM. Toshiba and Sony or whatever it's been.
Okay,
So,
okay.
Okay, IBM is...
We'll think about it the next time we get some money to buy hardware for.
So, any further questions on this great survey and pep talk? Because that will leave us, if we continue, we will have about 5 minutes to discuss the whole meeting. And we have a number of options. We can do general discussion. We can discuss the separate fields. We can discuss the separate techniques. Or you can return to your haranguing of Paul, you guys. Which do you want to do? You want to hear them argue with Paul some more, or should we press on?
I don't want to harangue Paul, although I wouldn't mind hearing, like, why the shock accelerates at the density gradient.
Well, that's protected, I think, for now, everyone is shot. But, and you had a point with him that...
Discuss it here.
Okay, and he was complaining about lack of vorticity with questions. But anyway, those are important points, and I hope you'll take them up at the next meeting. And now the question then is, where have we gotten? We have, I think the main point is Oka tells us we can now do a lot of things that need to be done, which is great. But I, for one, I'm still a little lost on a number of issues. Today, for example, we were talking about what's going on in the cosmology, and in cosmology I was interested in these people saying singularities in density form, the correlations form of galaxies' positions. I didn't hear any of those words, and yet everything's being computed. So what's going on? Paul, you're going to tell us.
Well, first, I think we may have made a mistake in the interpretation of since so much of the connection between reionization, the epoch of reionization, and the big picture of cosmology, questions like the power spectrum of fluctuations, the amplitude of the fluctuations, the scattering of CMB photons and projections for the future, surveys of 21 centimeter background. All of that stuff is cosmology, but I guess we came here thinking if it's weak R-type ionization fronts propagating over these vast distances faster than the gas can move to respond to it, this wouldn't interest you guys, so let's just talk about,
Okay.
the feedback.
So I am wrong to be asking about forests when we're talking about trees. I accept that remark, and I'll go home and think about these issues as well. Is anyone prepared to say any further remarks? Axel, have you got a last word of encouragement for us? Do you feel that you can say further. In that case, allow me to call on Oka's former student Boris, whose name I can't pronounce at the moment, that's my present condition, I'm a little exhausted, who has a few words to say. I hope Oka doesn't mind us springing this on him. You have about 10 seconds. No,
10 seconds.
Okay. 5 minutes.
5 minutes.
5 minutes.
Okay. This was, it says on with very small characters on the invitation that this is actually partially because of Oka's 60th birthday. And I was supposed to give a small talk yesterday, but of course Ben Gustafsson, as he always does, cuts me off and says I'm a very bad speaker. And then he stands there and says he says it's very easy to follow me because I give such bad speeches. And as all of you now know, he's an incredibly good speaker, so there's no way you can give a talk after Ben Gustafsson, because he always comes up with nice speeches. But I have a few comments, since I've been one of Oka's students, and most of you have been a co-worker, so I thought that he should have a sort of a take on how it is for his students, because there's not that many comments. We've heard a bit from one of his postdocs, and I'm gonna work a bit on that. Luckily, one of Oka's bit, let's say, funny ways of speaking is that when he gets up in public, and it's been a very complicated workshop, and everybody's completely, I have no idea what's been going on, Oka stands up, and luckily he's done it again today, and say, it's trivial. And you sit around thinking, I better think about that for a while. So that's one of his really good points. Sometimes he has the time to actually explain it to you, but most of the time he doesn't. So, now for my own sake, and I think some of his students has made the same mistake as I, when I started as a master's student, in Copenhagen we have to take a number of courses, and the only course Oka was teaching at that point was numerical astrophysics, or it was called computer physics at the time. And I thought this sounds pretty good, because I'm definitely not going to be an observer, it's way too complicated. There's like dark currents and all that sort of stuff, it's impossible. So I thought, well, computer physics, that's probably nice. I mean, I played around with Windows and that sort of stuff, so it'll be fine. Of course it wasn't. I was told later that Oka had this plan for his courses that because at that time the average pass percentage at the courses in Copenhagen was it was around 2/3. So about 2/3 of the students that actually attended a course would pass. So Oka had this very strict limit that if more than 2/3 of his students actually passed his course, he would make it more difficult next year, of course. So it sort of built up a trend of extremely smart people taking his course, and it just got harder and harder. So unfortunately, when I took this course, I ended up in the wrong 1/3. But luckily, Oka has so many students that he couldn't remember me when I told him I'd like to be his master student. Now, I wrote my master's...
I remember you now.
I have told him, and he's not too angry, I don't think. When I wrote my master thesis, Hans Günther Ludwig was in Copenhagen as a postdoc, and he had these 3 rules, Oka's 3 rules. I've got a couple of things that he forgot. First of all, he forgot one time of the week where Oka was not available. It was Wednesday at 3 o'clock. He went for tennis.
Tuesday.
No, it wasn't Tuesday. Was it Tuesday? Tuesday. There you go. I work too much. I guess. As he also said yesterday, it's hard to get in contact with Oka if you do not have a very intelligent question. The first email I got from Oka when I started asking him about things, he'd given me the 2,000 line code, and I knew a bit of basic, so he handed me the 2000 line Fortran 77 code and said, read this. And I had no idea what was going on. I couldn't compile it, I couldn't run it, I couldn't do anything. So I asked him, so what do I actually do to compile? And he sent me 4 letters back, RTFM. Now, for those of you that's been around on the web for a while, it actually means read the fucking manual. So I didn't understand that at the point, so I kept on writing emails asking him what's going on. And finally, I actually caught him in his office, and he told me he has this other method, which is called the Polish stack. Those of you who have pocket calculators probably knows of the Polish stack. You go into the stack, but that doesn't necessarily mean that that number is actually used for anything. So it sort of piles up in the Polish stack and you end up somewhere and you might never actually get to you, unless it's a very intelligent question. And that brings me to this lighthouse effect that Bengt was talking about. It's very true, Oka has this extremely narrow beam of what he finds interesting, and he shifts it at times. And he's been around a lot. He's even done plasma physics. We've just heard of, I don't know how many subjects he's been involved in. And the first 6 months, I was a bit sort of worried because I had chosen a subject he'd never worked on before, which was interstellar medium. And so I was a bit worried that he just sort of ignored me because it was a boring subject. But then I started coming up with a few results, and all of a sudden this beam points at you, and you're a bit like a moose up in the Swedish forest. So you stand around there, and all the light hits you, and you just sort of freeze. You have no idea what to do, and he keeps asking you questions which you cannot answer before like a week later. So both being outside of the beam and inside of the beam, it's quite a shift, but both are pretty scary. I don't.
True when you're a collaborator.
It's probably even more true, yeah. I don't have much more to say, to be honest, Oka, but it's been a pleasure to be your student, and I'm sure most of the ones that have actually been your student or is a student of yours feels the same.
Well, I have never run a meeting in my life. I've never hoped to see one, but I've been his assistant. And I can tell you that although he looks like nothing is happening, it's because he's got infinite energy. He doesn't sleep very much, I think, or when he does, it's hardly noticeable. And yet the meeting has gone beautifully. I think it would be hard to say that there was anyone here who didn't learn a lot, who wasn't very happy with everything, that things went smoothly. So I would like to express my thanks, and I wouldn't be surprised if I speak for all of us when I say thank you, Axel, for a wonderful and improving week, or 3 days, I guess it is only. It just felt like a week. Thank you very much.
Thanks, Ed. And with these words, I would like to come to a close of this meeting, but let me myself thank a few people here. First of all, Åke for giving us a very good excuse for actually running such a meeting. That's the first thing. The second thing is the audience for coming together here, all of you, to actually make it such a successful workshop. In particular, what I enjoyed was the diversity of the threefold diversity of the 3 different topics, which really had all three of us, all three of the different groups together for the entire period of the time meeting. I think that was another very good thing. Also, of course, I need to thank both Naudita and the ESF, the European Science Foundation, for providing funds to us. And Then, of course, I thank the scientific organizers, that is Ed, and it's Harald, and it's Orke, and it's Jörn, who has to be on a meeting since yesterday, and it's Yuri Polterman. Is he still in? Went away. Right, so that was the scientific organizing committee, and then there's a local organizing committee which was not officially mentioned, but that consists of those who helped me, especially towards the end of everything, which includes Jakob Trier Fredriksen and Petri Capula. It's over there at the end. Without their help, it would not have been possible to get the final revisions of the program into place, into shape. So that was done on the last night. And then let me thank, of course, those who made it technically possible. This is Gösta, who has been in charge of running the equipment, audio-visual equipment, and Hans, who has been putting up, Hans von zur Mühlen, who has been setting up the posters in advance, so that we had that we knew both of where both the Nordea building was and where the main building was. And then, of course, I thank Anne for such an infinity of work that you have been doing and are still continuing to do, which really is, of course, a tremendous amount of effort. That's because the Swedish tax authorities require all of us to hand in the passports and stuff like this. So, Anne, thank you very much. You all a good home, and Pavel does something, and before I give them the word to Pavel, what? Okay, she's still taking care of it.
While he's setting up,
before Pavel has something to say,
one thing to say, now for something completely different, at 6 o'clock next door, you get a lecture at the Astrobiology Institute about the habitable planet, where they're probably at this very moment having a meeting about radiative.
Okay, so there are two things I want to say. The first is I want to give some advertisement for another workshop on radiative transfer, which will be taking place in the beginning of September in Durham. And the idea actually here is so it's not to replicate this workshop, but actually have maybe 1 or 2 talks on a day, and the rest of the time really sit together and work on different things. The intention to some extent is also the same, that we don't want to exclude sort of only have cosmological radiative transfer, but actually have some crosstalk between the different disciplines. So here we mostly telling each other what we're doing. There we may actually be able to interact a bit more. I think it hasn't been announced on the meeting's website yet, but that's why I wanted to give a little bit of attention. So the main organizers, Tom Towns and Richard Bauer, who are both at Durham, and then it's Benedetta Charlie, in Garching, and myself, who are setting this up. The other thing is that we now hope to have a discussion about the comparison project that was partly presented this morning. So everybody who's interested in that, I hope not too many, because we'll be going to a smaller room upstairs at the Astronomy Institute. But everybody who's interested in following should sort of gather around me, and then we'll go upstairs.
But this is cosmology, right? This workshop will be about cosmology transfer.
No, not necessarily. I think it's not. We are trying to involve other stuff as well. It is at the ICC in Durham, but the idea is that, I mean, it's yeah. Okay, those were the two announcements.